video, we are going to see Cayley's formula for finding the number of spanning trees for a complete graph on n vertices. So, the proof of this theorem was developed by Proofer in 1918, and already we have denoted the number of spanning trees of a graph G to be tau of G. So, here you have tau of Kn. We are calculating the number of spanning trees of the complete graph Kn. So the statement is this: tau of Kn is equal to n raised to n minus 2. It is a very simple statement and we are going to prove it. Suppose you are denoting the vertex set of this Kn to be capital N, and we know that there are n vertices for Kn, and we are giving them the notations 1, 2, 3, etc. n, that is capital N. Okay. Now we are just going to define a sequence of length n minus 2 such that the entries of the coordinates are coming from this set capital N. Okay. Suppose if capital X is equal to the set of all such sequences with n minus 2 coordinates, n minus 2 tuples, the entries coming from N. Okay. The cardinality of X is equal to, how to find it? We have, see, n minus 2 coordinates. Each coordinate will have n possibilities coming, right? So how many times this n possibilities? N minus 2. So n into etc. n minus 2 times, that will be n raised to n minus 2. So cardinality of X is equal to n raised to n minus 2. Suppose Y is the set of all spanning trees of Kn. Okay. So we have to prove that cardinality of Y is equal to n raised to n minus 2. That is our basic aim, because we have to show that the number of spanning trees of Kn is equal to n raised to n minus 2. So presently it suffices for us to prove that cardinality of X and cardinality of Y are the same. Okay, instead of proving both cardinalities are same, we have to just show that X and Y are having one correspondence with each other. Okay. That is, there exists a one-one correspondence between the set of all spanning trees of Kn and the set of all sequences we just mentioned before. So we are taking T to be a spanning tree of Kn, and we are trying to associate a unique sequence T1, T2, etc. Tn minus 2 by defining as follows. Suppose N, the vertex set, is treated as an ordered set, okay, where order is very important. Okay. Suppose S1 be the first vertex of degree 1 in T. So since T is a spanning tree, it's a tree, we know that every tree will have at least two vertices which are having degree 1, the existence is guaranteed, and with the order of n, 1, 2, 3, etc. n, suppose S1 is the first smallest number among the vertices which is having degree 1. And definitely that vertex will have an adjacent vertex, and that vertex is taken to be T1. Okay, so we got the first coordinate. Now delete S1 from spanning tree T. So when we remove S1, the corresponding edge that S1 is adjacent to, that will also go away. Okay. Now suppose if S2 be the first vertex of degree 1 in T minus S1. So the vertex adjacent to S2 is taken as T2, and we are repeating the operation till we obtain Tn minus 2, and a tree with just two vertices is remaining. So in order to give an illustration, suppose if this is our graph, the spanning tree, you know that there are 8 vertices here. That means this is a spanning tree of K8. Okay. And for the spanning tree, you can see 1, 2, 6, 7, 8. The vertices are having degree 1. Among that, 1 is the smallest one. That is the first vertex having degree 1 according to the order of the set n. Okay. So you are choosing this 1 to be S1. Okay. Corresponding adjacent vertex is 4. So T1 is 4. So we got the first coordinate. Now you have to delete this S1 is equal to 1. Okay. When you remove one, the edge adjacent to it will also get removed from T. So T minus 1 will be the vertex, will be the graph here, this tree here. And for that, look at the vertices with degree 1 and 2 is the least among those vertices. So S2 is 2, corresponding adjacent vertex is 3. So T2 is equal to 3. You got the second coordinate. Then you remove this S2 is equal to 2 from T minus 1. So this is the remaining graph. From that you obtain S3 is equal to 6, correspondingly T3 is equal to 5, and then you remain this S3 is equal to 6 from the earlier graph, earlier spanning tree, earlier tree. Then you get S4 is equal to 7, T4 is equal to 3, S5 is equal to 3, T5 is equal to 4, S6 is equal to 4, T6 is equal to 5, and we obtain a position where we just have an edge remaining. Okay, so this is a tree with just two vertices, that is where we stop. And we have obtained till T6. We had 8 vertices, so 8 minus 2, 6 coordinates are obtained, and we can form the corresponding sequence like this. Sequence T1, T2, T3, T4, T5, T6 is equal to sequence 4, 3, 5, 3, 4, 5. That is what obtained here. So here we can also understand that each spanning tree will be associated with a unique sequence. You can just think why it is a unique sequence. Now, associating a spanning tree of Kn to a sequence, that is the next part. So, the earlier part, you can note that the vertices here 3, 4, and 5. 3, 4, and 5 are the vertices here, right? So, those are the vertices which are repeated, and the vertices which are missing are exactly those vertices which are having degree 1, right? 1, 2, 6, 7, 8. So that is an observation you got from part 1. Okay, so to prove part 2, the second part, suppose you have the sequence T1, T2, etc. Tn minus 2, you are going to reconstruct T from this sequence. Suppose if S1 is the first vertex of M not in this sequence, T1, T2, etc. Tn minus 2, then join this S1 with T1. Okay. And suppose if S2 is the first vertex of n minus set S1 not in the sequence with the first coordinate removed, T1 is removed. So you have T2 here. So this S2 and T2 are joined. And you are continuing this process until you are obtaining n minus 2 edges like this. Okay. And finally, T is obtained by adding the edge joining the remaining two vertices of n minus set S1, S2, etc. Sn minus 2. And also here for each such sequence, the associated tree which we are drawing will be unique. Also you can think about the logic why. Okay. To illustrate this portion of the proof, you are taking the same sequence we obtained earlier and going to form the same tree. So you have T1, T2, etc., T6 like that. Since we have 6 coordinates for the sequence, we should understand that 6 plus 2 is equal to 8 vertices will be there for the tree. So n is equal to 1, 2, 3, 4, 5, 6, 7, 8. And you will, here the position of the vertices are kept the same as for the earlier spanning tree, because we have to show that this the same tree is coming by this definition of forming the tree. So here you have vertex 1 is the first vertex of n which is not in the sequence 4, 3, 5, 3, 4, 5. So S1 is equal to 1. You have to join this S1 with 4. You have joined it. So S1 is equal to 1, T1 is equal to 4. Now you remove S1 from N. So you have this set. Now vertex 2 is the first vertex of N minus set 1 which is not in the sequence. So you have to join this 2 and 3. Okay, here S2 is equal to 2, T2 is equal to 3. Fine. Then you join 2 and 3. Similarly, in the next step, N minus set S1, S2. You have this set. 6 is the first vertex which is not in the set. which is first vertex in the set and not in the sequence. So you have x3 is equal to 6 and t3 is equal to 5, join them. Next step will be like this. You have s4 is equal to 7, t4 is equal to 3, so you join 7 and 3. And in the next step you have s5 is equal to 3, t5 is equal to 4, you join 3 and 4. And in the next step you get s6 is equal to 4, t6 is equal to 5, you join 4 and 6. 4 and 5, t6 is equal to 5, that means you are joining 4 and 5, and now you have obtained 6 edges. 8 minus 2 is equal to 6 edges. And to obtain the final t, t is obtained by adding the edge joining the two remaining vertices of n minus set s1, s2, s3, s4, s5, s6, and that will be equal to 5, 8. So join 5, 8, and finally you obtain the same spanning tree as that we had earlier. So that's how we can prove Cayley's theorem with an illustration. Thank you for watching. See you in the next video.